So last time we talked about how to find the derivative, the definition of the derivative as a function, the derivative function. And so we did an example using this limit definition. I'm not going to do a ton of examples in the notes. We spent a whole chapter on limits. I've picked what I think are some of the harder ones to do in the notes that often, radicals, things like that, as opposed to just polynomials. But I'll be always happy to go over them during our Zoom class sessions. So last time, here's the typical kind of sequence of a real common question, what's the derivative using the definition? Then use it to find the slope of a tangent line and an equation of a tangent line at a specified point. All right, we ended with an observation though about the domains, that the domains of f and f prime are not always equal. And when we talk about the domain of f prime, another way to refer to that is we'll say that that is where a function is differentiable, is essentially where the derivative exists. So what we want to do now, I'm going to kind of start this section and then we're going to kind of go to the next page and come back. We're going to kind of weave these next two topics together a little bit. So what we want to talk about is the relationship between graphs of functions and their derivative functions. And so first, let's just start with this basic idea. So, what is the derivative at a point? Well, it's the slope of the tangent line at that point. So if you were to take a graph of a function, so notice this one in blue, it's, some sort of degree 3 polynomial here. If you were to find all of the slopes of the tangent lines at any of these points, and then graph all of those slopes, that's what forms the graph of the derivative. So as you look at, for example, let's say right here at -4. Okay, so right there at -4, okay, it looks like the slope of the tangent line. Now remember, the slope of the tangent line, that's the derivative. So it looks like f prime at -4, this looks like a pretty steep slope. And I'm cheating a little bit because I'm looking at my graph of the derivative down below, but that is this slope. So the slope of the tangent line at x equals -4 is equal to 6. So that is this slope right here. The slope of that line is 6. Well, guess what? That is literally what it means to say, what did I just write out? F prime of 4 equals 6. So that means on the derivative function, f prime at -4 gets plotted at 6. So all of the outputs on the derivative function, all of those outputs represent what the slopes of the tangent lines were on the original function. So 6, this 4, so that corresponds to the slope over here at 3. So if I was to draw or look more closely at this slope at 3, this is saying f prime of 3 is equal to 4. Well, that is exactly just saying, then when I graph my derivative function, f prime, guess what? At 3, we're located at 4. So that's the relationship, right? Now, let's make some generalizations. So let's start with a region that's not even on this particular example. So just kind of think reasonably, if a function is constant, what would its rate of change be? What would its derivative be? And hopefully that comes relatively quickly. It's okay, that means it would be equal to 0. So if you were to think about maybe this on a graph, so if you have a function or a region of a function that is constant, so let's say you're looking at the function f of x equals maybe 2 or something, its rate of change is 0. So that means its slope, so when you think about this function, you're thinking that the rate of change of a linear function is always the same. its rate of change is equal to 0. All right, so what would that mean then on the graph of the function? So on the graph of the derivative of the function. Well, where is 0 on the coordinate plane? Well, that's the x-axis. So it would be actually on the x-axis. So if we were to graph then this derivative, its derivative would then be, so then we would say this would mean its derivative would actually just be at 0. It would be on the x-axis. Okay, so that's what we're looking at there. I'm going to erase some of this because I just don't want this table here to get so cluttered, but that's the line of thinking on that one. All right, now let's think about where a function is increasing. So look at the two kind of areas that we've already highlighted in that like purple color. When the derivative, when the original function is increasing, in that situation, the derivative is positive. So it has a positive rate of change. If you were to think about all the little slopes of the tangent lines, if I was to draw, a tangent line here and a tangent line there, or over here, if I was to, continue to draw tangent lines, whenever the function is increasing, the slopes of those tangent lines or the rate of change of the function is going to be positive. So if a function is increasing, that means f prime is going to be positive. Well, what does positive look like? That means on the graph, these regions are going to be above the x-axis. That's where positives live, are above the x-axis. Okay, so let's think about, again, I'm going to kind of erase some of our earlier, earlier observations here. And so let's kind of summarize this one. Excuse me. So places where a function is increasing, regions where f of x is increasing, means that f prime is going to be positive. So down here on f prime, I'm above the x-axis. I'm positive. I'm above the x-axis here. All right, places then where a function is decreasing. So if you're decreasing, think about if you're going to draw in like the slope of the tangent line here, or if you were to draw in the slope of the tangent line there, or the slope of the tangent line here, all of these little slopes of tangent lines would be negative. So those are the values, like if this tangent line right here, if that has a slope of -2, then that means on the derivative, that point gets plotted at -2. So all of these regions in a graph where a function is decreasing, that's a negative slope idea. It's a negative rate of change. So regions of an original function where the original function is decreasing. So this function's decreasing from here to here. That's going to mean that on its derivative, those were all negative rates of change, so the derivative is negative or below the x-axis. So negative on f prime or below the x-axis. All right, so I really don't need these arrows if I'm writing it out in words, do I? So this is going to mean below the x-axis. All right, places of horizontal tangent lines are where the slope is equal to 0. So if you think about going back here, places where you have a horizontal tangent line, right at that one point, the slope is equal to 0. Again, right at this one point, the slope is equal to 0. So that means those particular points go to 0 on the derivative. So horizontal tangent lines are going to go to 0. In other words, they are going to be right on the x-axis, or they'll be like x-intercepts. Okay, so we're going to stop, we're going to fill in the other parts in a little bit, but let's stop with those first 4 observations, and let's take a look at a couple of the simpler graphs that we have here, like number 1, let's just take a look at. Now, as we look at this function, we want to think about all the things that we just talked about up above. So, you kind of have to start with some fact. A lot of times a common fact that we might start with is the last one we did, which is to say horizontal tangencies go to 0 on the derivative. So suppose I thought that the function in blue, suppose I'm like, I don't know, I'm going to guess. And my first guess is going to be that the blue function is f and the black function is f prime. If I think the blue function is f, places where there is a horizontal tangent line, those need to go to 0 on the derivative, and it doesn't. So that means this is wrong. So really from this one fact alone on this example, I'm going to be able to make my determination. So I have 2 places where I have a horizontal tangency. So this is a location of a horizontal tangency. If I'm focusing on the original function being the function drawn in black. And here's another point of horizontal tangency. Those then go to 0. They go to 0 on the graph of the derivative. And so this is telling me that the black function is f and the blue function is f prime. But there are the other observations should all make sense as well. So remember, we also said that where a function is increasing, so where f is increasing, and there are 2 intervals where f is increasing means a positive rate of change. So those regions should be positive on the derivative. So positive meaning they live up above the x-axis. Regions where f was decreasing, these are negative rates of change, negative derivatives. So this should be negative on the derivative function. And so that also makes sense. All right, so that's like a basic example. We'll come back to number 2 in a second. Let's take a look at number 3 here. So number 3, I can't rely on any of my zeros, maxes, where the horizontal tangency go to 0 or to x-intercepts, because I don't have any of those here. So I need to rely purely on the information about where a function is increasing, its derivative is above the x-axis, and where a function is decreasing, its derivative would be below the x-axis. If I thought the red function was maybe the original, the red function is decreasing. Its derivative would need to be entirely negative or below the x-axis, and the green function is not. So that leads me to believe, and then we will test it out, that leads me to believe that the original function f is going to be the one in green, and f prime will be the one in red. All right, so let's test it out. So remember, where an original function is increasing, so where f is increasing, which it is everywhere here on its whole domain being shown, so where f is increasing, the derivative needs to be positive or above the x-axis, which it is. So that does make sense.